Okay, good morning to all of you. Today we'll discuss about the basic concepts of voltage source converter. Actually, this is in the chapter 2. First chapter or unit is completed. There we have discussed a number of uh, points related to the introduction to facts controller. We'll go back and review that introduction and we'll discuss this voltage source converter concepts. See, in the first chapter unit, we have only the basics of facts controllers. In these basics, we have seen classification, benefits, and how or what are the control parameters which will affect the power flows that we have seen. Then basics of AC power flow in a power system. Either we have taken a simple single machine system or two machine system you can take, and we have seen the power flows, real and reactive power flows, phasor diagrams, everything we have discussed. And the limit, actual limit of the transmission line, or what are the factors which will limit these transmission power, that we have discussed. Okay, I'm repeating. Basics of power in AC system. There we have discussed in detail about the power flow in parallel systems, machine network, and also the different phasor diagrams related to that one. And the concept of facts controllers are introduced, and how they are changed the characteristics of transmission system that we have seen. Okay, generally we'll discuss review. Okay, generally if you consider a power system, simple power system, it has a generation, transmission, distribution. Utilization also you can consider in the distribution system. So mainly these facts controllers are used in the transmission system. Our name itself indicates that flexible AC alternating current transmission systems. Of course, controllers are devices. These are devices or controllers which are used to control the power flow, both AC and DC. That is the main concept. Facts, flexible AC transmission systems, devices or controllers. Then how the AC power is controlled, or what is the AC power flow? If you consider a simple power system where a single machine connected to a load or infinite bus bar, if you consider it as a simple load, that is called it as a standalone system. A simple generator connected to a load. Even in our laboratory, we are doing alternator experiment, which is connected to a motor again. Mechanical power is given to that alternator and generates power, and you can give it to the load or OCSC test you might have performed. So that is that experiment we are doing in laboratory. That means a generator is connected to a load directly. Alternator is connected to a load. That is taken as a simple power system. Simple, the standalone. Or if it is in a synchronization experiment, it is connected. That same machine or the alternator is connected to the bus bar. That is APSCB supply, synchronized by different using different methods that are not important. But while synchronizing, we have seen the voltage should be, magnitude should be equal, and frequency, and that for the frequency we have seen okay, different methods. Okay, that is okay, by changing the field of the primary mover. Okay, field winding, we have changed the frequency of this one, which is matched to that one, and that we have closing will be done at same instant where the uh, there is no difference in the voltage, otherwise it will damage. Okay, so that's why synchronization method is different. Okay, there we are synchronizing the existing alternator to the infinite bus bar. In phase sequence also we have seen. Okay, so these three, voltage, frequency, phase sequence, we have seen. But here the instant at which you are synchronizing, that is also important. We have seen different methods, but that is okay. So that is also taken as a simple power system. That means alternator connected to the infinite bus bar, nothing but here APSD supply, board supply we are considering. So in that case, you can vary the field winding of the prime mover, that is the speed of the alternator, but it won't change once it is synchronized to the infinite bus bar. Even if you are trying to change the field winding, their frequency won't change, because the infinite bus bar frequency is constant, irrespective of the number of generators are connected to that. So if you consider a simple transmission system in between that, so that resembles the simple power system. There you can vary the real and reactive powers. You can calculate that. Different methods are there. We have calculated the real and the reactive powers of the machine, or the transmission system. So mainly the formula for the real power everyone has to know. That is V1 V2 by X into sine delta. This is basic one. The power flow in the transmission system, it depends on the potentials, sending end 1 and receiving end 1, V1 V2, and the sign of the angle between these two phase voltages, these two voltages, that is the phase angle difference, delta, and reactance of the transmission line or impedance of the transmission line. So here we have considered lossless transmission line. If you consider resistance, definitely losses will be more. I square losses will be there in the transmission system, so that the real power sending end is different from real power received at the end. Okay, but here we are considering the ideal transmission system. There only reactance is considered. So difference in reactive power will be there at the sending end, receiving end, whereas real power is same, that is given by V1 V2 by X into sine delta. Please go through this formula and you derive on your own. This is important. Then okay, here the concept of series compensation, phase angle regulator, or a static phase shifting transformer. Actually, that concepts were not there. Static phase shifting transformer concept was not there in our syllabus, but it is easy. You can see that is analysis point of view. We are changing simply delta, sine delta. P is equal to EV by X into sine delta. If you see the uh, if you see the relation real power, so that is equal to V1 V2 by X into sine delta. Okay, this is very basic for power flow. See, everyone has to derive. Once you derive, then you get the confidence. Okay, V1 V2 by X into sine delta. So here by changing delta or by changing X value, you can alter the real power directly. You can see that when delta is small, sine delta is approximately equal to delta. So that by changing delta, increasing or decreasing, P will be decreased or increased. So similarly, X, by increasing, you can decrease P value. By decreasing, you can increase P value. That is inversely proportional. Same, this concept is okay taken even while considering the parallel paths, power flow in parallel paths. That is basics of power flow in AC. We have seen basics power flow in parallel paths. There we have taken two different values of X, and how the power is flowing on two lines we have seen without any controller. Later, we have introduced FACTS controllers or HVDC, so that the power on one is controlled, so that the other remaining power will be flowing through the other. So that is as desired by us. Okay, so that way you can control real. Similar to this one, reactive power is also Q is equal to V1 into V1 minus V2 cos delta by X. There also power is reactive power is directly proportional to V square by X. There also by changing X value can change the reactance, but the effect, okay, once you change the series compensation, the effect on the real power is very high. Or by changing delta, the real power will be changed sharp, or the main effect will be there on this one. The reactive power flow will be less affected with the changes in delta. Okay, they, we change the we inject the currents in that case, that is reactive power compensation. So that is about basic concept of AC power flow. We have seen phasor diagrams, and the real reactive powers are calculated, and how these parameters have effect on this one we have seen. Then finally, okay, we have uh, classified the FACTS controllers into four types. One is series FACTS controller, shunt FACTS controllers, combined series FACTS controller, combined shunt and series FACTS controllers. So these are the four controllers we have discussed with examples also, and how these real and reactive powers will vary with that FACTS controllers also we have seen briefly. Okay. Then classification, benefits we have seen. Number of benefits are there, starting from real and reactive power control, and reactive power decreases, that is compensation is there, reactive power compensation, so that on the same existing transmission line you can send extra real power. Then the capacity of the transmission line, that is the loading capability of the transmission line is increased with the FACTS controllers. If you place an ideal FACTS controllers at the midpoint, the capacity of the transmission line will be doubled. Ideal one, once you consider ideal regulator, that is FACTS controllers at the midpoint of the transmission line, and if you take each segment, that is up to midpoint and midpoint to end, then each segment power handling capacity will be doubled. So that we'll discuss in the objectives of shunt compensation and other. Then the capacity of the transmission line again depends on the uh, three parameters. One is thermal, second one is dielectric, third one is the stability considerations. Thermal means mostly physical parameters, sag, temperature, the distance between the poles and other wind velocities and other. Okay, they are not so important. Okay, that you can adjust. Okay, but whereas coming to the stability considerations, okay, transient stability, steady state stability, dynamic stability, voltage stability, frequency stability, and subsynchronous resonance, these are all important. Whereas the voltage stability is also considered in the dielectric capacity, that because every transmission system is having additional capacity. Even if you take example of our own, okay, you can handle, you may have the capacity of handling up to 40 kgs you can carry, but for a very short duration, less than 1 minute or half minute, even you can handle 45 kgs or even 50 kgs. That is the short term capacity. Even in the utilization chapter or the drive chapter, you will give the ratings, continuous ratings, intermittent ratings, short-term ratings of a particular machine, depending on the heating and cooling. So similarly, this one, even anything transmission line is also expected 10% over voltage sometimes, but it won't have any effect to the transmission system. But frequent overloading, that is frequently, if that experience over 10%, then the life of the transmission system will be damaged. Otherwise, for a short duration of time, even 10% of extra voltage, if they get, nothing will happen, because it has, even while designing that or manufacturing that component, they take care. They have they design with additional this capacity. Okay, so that is about the thermal capacity, dielectric constant or capacity, and stability considerations. In detail, stability analysis we'll see later. studies in particular transient stability, because these facts controllers will have effect on the margin of the transient stability. It will increase the margin. The margin means a simple space or area in a equal area criteria. That area you can increase capacity. That is the stability margin you can define. Transient stability margin that is increased with this facts controllers. So stability will be improved, security will be improved, power handling capacity will be improved, real power is increased, reactive power is decreased, losses are decreased, and power flow, real and reactive power flow is controlled, reduced loop flows, and upgradation of lines, and flexibility while placing the new generations. But nowadays, already we have discussed the penetration of the renewable energy technologies is very much high. Okay, you can see that already 40% or 30 to 40% in a distribution system. It goes on increasing the renewable energy. So the existing, sometimes the existing transmission line has to carry the extra power. Once, for example, if you take in near to Karnoolu, okay, Kadapa, near to that, the number of renewable energy solar power plants were installed. Okay, they are then with that, okay, you have to, sometimes you require to transfer that power over the lines with the existing one. Okay, it is not possible to install a new generation, a new transmission system again. Okay, so that's why this is with the facts controllers, this is possible. Okay, this is possible. Okay, so layout, that is a flexibility for a selection of the site for new generations are possible, and already discussed. Okay, and already the entire power system is connected. Remember, India, though different grids are there, power grid is taking care of these interconnections. So the bilateral transactions between different grids, they are taking care, so that the cheap power, for example, in a deregulated environment, there is a flexibility. You can generate power far from the load center, and you can trade it. You can or you can take the same power at some other point yourself. You can take the power. Okay, that is the advantage in a deregulated environment. Just you have to pay the rent for the transmission line. That's all. You need not. Okay, that is the advantage of deregulated environment. Number of private players, Adani Power, Tata Power, Reliance Power, like that. Number of private players are coming into this industry. Now, if you see that emerging technologies like mobile portability and other number of players are there, the BSNL, Airtel, Geo, like that, number of private players are there. You can choose any plan, any mobile option you can choose. But here you don't have any other option to choose. You have to go for only APS-CB board power supply. But in future, with these emerging technologies like mobile selection, okay, there you can choose the operator. You can choose the Reliance Power, you can choose the Adani Power, you can choose the Tata Power, okay, for our house. Okay, so in future, with these emerging technologies and deregulated environment, that will be possible, so that competition will be there between that players. But here only monopoly, only the state government electricity board is there. That is the major, it will play major role. We don't have any other option. But in future, with this like mobile technology or mobile SIM card, you have the flexibility to take power from the different players. In the case of emerging technologies, with these facts controllers, it will be possible. It will be possible. And in a deregulated environment, number of private players are there. They are generating and they are selling. They are simply, okay, they are with for a different operators. Okay, that is different. Okay, so that transactions are going on like share market trading. You can see that the power generation, for example, Tata Power, they want to sell the hundreds of thousand units for 3 rupees, or they quote 2.5 rupees. If anybody is there in the market who is willing to take with that price, they will quote so that the transaction will be executed. So this is happening in a deregulated environment, or it is happening now. Even our APSB supply, the load dispatch center is there at Vijayawada, Vidyut Chauda. They are purchasing power from the others using this way. So that is possible in a power exchange. IEX exchange is there. Okay, like Bombay Stock Exchange and Nifty. Okay, we have IEX power exchange. We have. You please go through that one, the latest technologies and other. Okay, today we'll move to the other basic concepts of this voltage source converter. For other actual scenario, number of facts controllers in the entire world or in our India, how many are there, where they are placed. So these things we'll discuss further. Okay, and I will similar to last year, last semester. You are welcome to present any seminar if you are interested. Remember, okay, if you are interested in any of the particular topic, you are welcome to give presentation for 5 to 10 minutes. Okay, so that also we'll see, okay, in the next coming classes. So this is actually the voltage source converter. This is actually the second chapter. So we are moving into the second chapter. So many of the things are discussed in the first chapter, and the lastly, only three important points were given. That is requirements and characteristics of power semiconductor devices, and also the different ratings, VI ratings and power trade-off, parameter trade-off. We have discussed, and then speed of the switching and the losses we have discussed, because all are important. Cost of the facts controllers depends on the power switching device cost and protection equipment and losses, everything. Lot factors will be depending once you consider the overall cost of the facts controllers. Okay, so in this class we discuss briefly about voltage source converters. Next class in detail analysis we will see regarding this voltage source converter, single phase, three phase, and what are the different switching devices are used, how they are okay placed. Okay, that okay. See, converters are classified into two types. Here, voltage sourced converters and current sourced converters. VSC and CSC, current sourced converters. In a short form, we'll take, okay, VSC, ISC. 90% of the facts controllers, they use the voltage sourced converters as an integral component, basic component. In second or third phase of third generation facts controllers, what are they, you may ask. Okay, see, in case of first generation facts controllers, simply we use thyristor valve or switch, only one, along with the energy storage devices like inductor or capacitor. We use inductor, okay, to reduce the generally once if you have extra voltage, okay, or we have extra reactive power to compensate that one, we have to place inductor. If you place the inductor permanently, then sometimes, because reactive power will vary, current will vary continuously in the system. So similarly, reactive power is also varying. Active power, reactive power, they are not constant, because switching power system, if you see that, it is dynamic, and second by second the load is varying, so that accordingly the currents and all other changes will be there in the power system. So that here, once you place the inductor or capacitor permanently, then it is a problem, because sometimes the placing of this inductor will create a problem. That means the we require that extra compensation will be there sometimes, or once you require reactive power, you can place capacitor. So if you place extra capacitor, then that is a problem. So once you want to vary the capacitance and the inductance as per the requirements of the reactive power or the transmission system, then it is advantage. So for that, we are going for a switching, thyristor switching, okay, or the devices which are used in the along with the thyristors are GTOs and other thyristor IGBTs we use, and MCTs, okay, that is metal oxide semiconductor thyristors, MT, okay, turn off thyristors, MTOs we use, GTOs, and integrated gate commutated thyristors, integrated gate IGCTs are also we used. We along with existing one, you can use okay. We can simple SCR or thyristor we SCR thyristor we use, and then GTO, GTO, gate turn off thyristors, MTO, metal oxide, turn off thyristor, and metal oxide semiconductor turn off thyristor, and integrated gate commutated thyristor. Okay, gate commutated thyristor. So these are the four that generally we use. Okay, that is along with SCR. Uh, Thyristor or SCR we can call. This is the basic one where you will have only in the first device will have only the control on only, that is switching on only, whereas the other three, gate turn off thyristors, MOS turn off thyristor, and the integrated gate commutated thyristor, okay, all these three we have turn off characteristics. That means turn off is also possible with the gate. So in the first case, it is not possible. Only you require to design a separate commutation circuit for this SCR or thyristor, whereas the other three using they are also called as turn off devices. Turn off devices. They are classified as turn off devices also. So in this voltage source converter, we use this GTO. You can see that okay, because here again this SCR, GTO, MTO, IGCT, the first one is having only, I will explain now, okay, only control on turning on, that's all. But whereas the other three devices, they have the control on and also off. So these three are called turn off devices. So these this turn on device you can call, are okay, they are also called as a turn off devices. So these three are called asymmetric devices, okay, and generally these are used in voltage source converter. Okay, you can use symmetrical also, but whereas in case of voltage sourced current sourced converters, you have to use only this symmetrical type, okay, that is SCRs we have to use. Okay, see in the case of voltage source converters, we can use anything generally, okay, but should have the, see here the GTOs or MTOs or IGBTs or IGCTs, okay, so these are all are having turn off characteristics, and all these are having anti-parallel diode. You can see that they are having a anti-parallel diode with this switching device. You can see that here a GTO is connected anti-parallel to the diode. Okay, this is used as a switch or valve for any of the, okay, current source converter or voltage source converter. We can take, oh, sorry, for voltage source converters, we cannot use these turn off devices. Okay, and remember that generally any of the okay voltage source converter, okay, used in the system, generally they are terminated by AC side of the AC side of the AC side of the converter is terminated by an inductor. Remember, this is also called as a filter, or sometimes it is connected via the coupling transformer. This here we connect to the power system using transformer. So the sometimes this transformer reactance will be acting as this inductor. You need not place additional or external inductor in the case of voltage source converter on AC side. AC side. Generally, the AC side of the voltage source converter is terminated by the inductor. The DC side of the voltage source converter is terminated by the capacitor, or sometimes the battery. Okay, very rare. Okay, or storage will be having here. So generally the AC side of the capacitor, okay, AC side of the converter is terminated by the capacitor. And remember that in the case of voltage source converter, the polarity of the voltage source, that is plus minus, it won't change. It won't change. Only the current directions will change. There are some important points related to the voltage source converters. Actual voltage source converters with single phase, three phase operation with waveforms, everything will discuss later. But you should know the fundamentals. Okay, which devices are used in the voltage source converters and current source converters, and why they are used, okay, and how they are used, okay, that you should know. So here the power exchange is possible, that is inverting or rectifying mode is possible with the change in direction of the current. Very similar to this one. Very similar to this one. Once you consider the current source converters, the AC side is terminated by a capacitor, a DC side is terminated by an inductor, and here we use the diode in series with the switching device. So that is SCR. SCR, they should have voltage blocking capacity, but that is having a current handling, reverse current handling capacity. Okay. So like that, their current is direction is constant. Here the voltage direction is constant, never change, never change. Depending on this current change, exchange of real and reactive powers are possible. Okay, so this way we'll in detail further analysis we'll discuss in the next class. Okay, uh, see, so this is the each leg how it is operated. Okay, how the in positive cycle, how that is how the this is current, how current is flowing, and whether it is a rectifying operation or inverting operation, everything we'll discuss in the next class depending on the firing angle. Okay, you can see the rectifier or inverter operation and firing pulse and the output voltage at this one. All these things we'll discuss, and the inverter operation, rectifier, and single phase leg, single leg operation also we'll discuss how this voltage or currents are varied with this one. Next class we'll discuss. With this I'm ending. I have some other work. Okay, so today I request please, okay, next class we'll further discuss regarding the uh, complete operation with different points. Okay, here small mistake is there in the in between. Here 3 dash, there is no direct connection. Okay, then I will also send the material, first unit material to you. So I have some other, okay, some so I am ending the class. Okay, sorry for the trouble created. Okay, thank you. Next class we'll discuss further this voltage source converter complete operation, how really these uh, power flows takes place, or how that control is happen with the firing angle control, and devices details in detail, and VSC will compare in a tabular column both VSC and CSC, and we'll see the differentiations, and only except one advantage inherently, the current source converter will have only one advantage. For a short circuit on the DC side, it won't have any current short circuits. Okay, that is short circuits, that devices won't have the additional protection. That is the only advantage that we have in the current source converter. Remaining all are advantages for the voltage source converters. That's why we use 90% of the effects controllers, this voltage source converter. So we have to analyze this voltage source converter in detail. Next class definitely we'll discuss in detail about this voltage source converter, and I will also share the material regarding this voltage source converter complete, including single phase, three phase operations with the waveform and everything. Okay. Thank you for joining. And if anything, if you want to share